Hi everyone, and welcome to this Lloyd's Lab Spotlight Series event on the impacts of quantum computing on insurance, where I'll be exploring both the opportunities and the threats, in particular the cyber threats to encryption posed by this emerging technology to the insurance industry. So what is quantum computing? The image you can see on the right hand of the screen is an image of a quantum computer. And as you probably noticed, it looks absolutely nothing like the laptop device that you're viewing this webinar through. And that is because quantum computing is a fundamentally different type of computing technology. It's based on the laws of quantum mechanics, which are the laws of nature that govern really tiny objects and can lead to all sorts of weird and wacky phenomena. And it can perform calculations that are not currently accessible to the computers we have today. So it's important to stress that quantum computing isn't just a more powerful version of classical computing, but it's an entirely different technology paradigm that can be used to solve problems we have no other way of solving with the computers we have today. In the words of Richard Feynman, I think I can safely say that no one really understands quantum mechanics. And so I'm not going to try and give you a physics lecture, but I do briefly want to touch upon how quantum computing is different. So in classical computing, information is represented by bits, which can take really well-defined values of either 1 or 0. So all of the images, emails, and even this video coming to you is represented by a string of 1s and 0s in a computer. However, in quantum computing, information is represented by qubits or quantum bits. And the difference is that qubits can have values of 1 and 0 at the same time, or any of the infinite combinations of the two. Qubits can also interact with each other via quantum mechanics. And all of these properties, plus a lot more, means that quantum computing can perform calculations in fundamentally different ways. And in some instances, this can give quantum computing an exponential speed up in solving certain type of problems. So why don't we have quantum computers yet, despite the enormous amount of development made in this field, particularly in recent years? Well, that's because there still remains some really complex hardware challenges. For example, the qubits that we spoke about, it's really difficult to keep them in the quantum mechanical state that they need to be to perform calculations. And with some qubit technologies, we even need to cool them down to temperatures below that of interstellar space. However, there's also been increasing investment globally, both in public and private sectors in this new technology. Firms received $450 million in 2017 and 2018, which was a $300 million increase from the previous 2 years. There's also been $22 billion in public national initiatives worldwide, with China taking the lead. We've also reached some really exciting milestones with this technology. For example, Google reached quantum supremacy in 2019, and just a few months ago, in December 2020, a group of Chinese scientists reported quantum advantage. And both of these terms mean that for the first time, it was shown that a quantum computer could solve a problem faster than a classical computer. Amongst them, quantum computing hardware players are the major tech companies. And there's also been a host of quantum computing software and service companies that have emerged in recent years. And this is really surprising given the fact that they are building software for hardware that doesn't even exist yet. But this just goes to show the confidence that exists in the emergence of this technology and how important it's going to be. And there are a lot of companies that are already trying to see what problems that they have that quantum computers can solve, and they're partnering up with these software and service companies to be able to find solutions to those. So I want to give you a few examples of the cool kind of things quantum computers can actually do. They might be able to help with drug discovery and design. For example, quantum computers might be able to simulate molecules and enzymes and proteins, something that we currently can't do with our classical computers. And this can drastically shorten the life cycle and cost of drug development, which on average takes currently 10 to 15 years. They can also be used to tackle climate change. And what I mean by that is that quantum computing can be used to address some of the most carbon-intensive processes we have by streamlining a lot of these processes. So 3 broad categories of problems that quantum computing is best suited to are optimization, simulation, and machine learning problems. And it's important to note here that quantum computers are unlikely to replace our laptops and smartphones, but they're more likely to be involved in a hybrid solution for solving particular problems. So bringing it a little bit closer to home, I want to speak about a few of the operational benefits that quantum computing can offer to insurers. For example, the ability to process a large amount of data might mean that they can help us gain a greater understanding of risk and improving pricing risk models. Quantum computing might be able to accurately simulate weather systems one day, which obviously has huge impacts on the insurance industry. It also allows the modeling of aggregate risks, which is something that's really hard to do with the computers we have today, just because of the number of variables involved in these problems. And so that can, for example, help with modeling of supply chain interruption, liability risks, or cyber risks. It will also, in general, improve machine learning capabilities, which in the insurance sector can help us with improved customer relationship management, fraud detection, and even better predictive analytics. However, as with any powerful technology, there are also consequences. And one of those consequences for quantum computing is that it can maybe one day be able to break the encryption systems that secure a lot of our data, from our emails and text messages to even government and military kept secrets. And the reason they might be able to do this is because of the way we actually encrypt data. So I'm going to show you for an example. If I gave you this number 15 and I told you to tell me the two numbers that multiply to give it, specifically the prime numbers, most of you could do that in a matter of seconds off the top of your head. 3 times 5. This is trivial for a human. But what if I gave you this number? You'd probably struggle quite a bit. And even if you had a handheld calculator, it would take you a while. This is really easy actually to do for our classical computers. But what if I gave a classical computer this number? Now, it turns out it's not just only incredibly difficult, but it's practically impossible for a classical computer to find the two prime numbers to multiply giving this in a reasonable amount of time. And that is what a lot of our encryption systems today, like RSA, are based on. They're based on the difficulty of solving these mathematical problems. But as we said, quantum computers can offer exponential speedups for certain problems. And one of those just happens to be factorizing large numbers into their primes. And just to put this into perspective, where it take a classical computer 300 trillion years to break a large RSA encryption key, it would take a nearly 4,000 qubit quantum computer only 10 seconds. And remember that the security of encryption comes from the fact that it takes so long to break it. So this is a real game changer. We can see that this can cause quite a systemic cyber threat to the insurance industry, because the type of encryption that quantum computing might be able to break can impact everything from the information we store in the cloud, to our emails, to the genetic information, to trade secrets. And so it can have huge implications. And because of the nature of cyber insurance, it can also impact other lines of business as well. For example, in intellectual property insurance, if the secrets of a company were stolen and then decrypted, cryptocurrency insurance can be impacted because blockchain is not quantum secure. There could also be product liability, recall, or BI insurance impacts if a hacker decided to get access to a 3D printer and decrypt the data and tamper. There could also be political risk insurance if state secrets and communications are decrypted. However, luckily, since we found out in about 90s that quantum computers might be able to break our encryptions, the world has also been looking for quantum secure solutions. There are some classical solutions to this quantum problem called post-quantum cryptography, and there are also some quantum solutions to this quantum problem called quantum key distribution. And both the NSA and GCHQ have been investing a lot of money in this and looking at how we can bring these secure solutions to fruition, as well as a lot of companies that have come up in the quantum secure space. However, as a business, if you're looking to use one of these algorithms for secure encryption, there's not really any standardization yet. However, bodies like the National Institute of Standards and Technology are looking to publish a set of standardized schemes between 2022 and 2024. But just because we might have quantum secure solutions one day, it does not mean that we're out of the woods yet. And this is because of something called harvest now, decrypt later. So remember that the entire point of encryption is that even if your data was intercepted by a hacker and stolen, it would not be any use to them because they wouldn't be able to decrypt it. It would just be scrambled. But what if somebody decided to hack your data today, intercept it and steal it, hold onto that data until a cryptographically relevant quantum computer was created, and then use that quantum computer to decrypt your data. Then your data might already be compromised today. And this is a huge game changer. So this begs the question, should we be worried as an industry? Should we be worried about the data that our policyholder keeps? And to assess that, I think we need to look at three factors. First, how long does your data need to be secured for? How soon is a quantum computer capable of breaking encryptions going to come about? And how long before we manage to implement quantum secure solutions? So if we look at the first two, this really alludes to the current threat, and these questions need to be used in the context of harvest now, decrypt later. So if you have a piece of information, or your policyholder has information that only needs to be kept secure for, say, the next 5 years, some credit card details are going to expire, and a quantum computer comes about in the next 10 years, then you're fine if somebody harvests your data today. However, if that data that's been harvested needs to be secured for 15/20 years, for example, military secrets or sensitive health data, and a quantum computer comes in the next decade, then your data could have already been compromised. And so that's something we really need to be thinking about. And then there's the other point where, of course, there's always the danger that a quantum computer capable of breaking encryption comes about before we've secured all of our encryption protocols. And that's a timeline that really we need to look at. And if history's taught us anything, overhauling entire IT infrastructures and implementing new encryption standards can take something like 20 to 25 years. And we might simply not have that much time. So what impact does this have on the insurance industry and the sort of questions that we need to start asking? Because the emergence of quantum computing is no longer a question of if, but a question of when, which means that the risk landscape has already changed because of retroactive attacks of harvest now, decrypt later. And so we really need to start asking some questions as an industry. For example, do we need to include any exclusions? Do we change policy wording depending on the shelf life of data? What do we need to do to secure ourselves against this? And also, of course, there's also the possibility that a quantum computer comes about before we've secured our data, which could wreak havoc on the insurance industry and lead to a systemic cyber disaster. And so what can we do as an industry to avoid that? How can we be part of the solution? Do we need to, for example, incentivize better cybersecurity standards amongst our policyholders? And so really the question I want to leave you with, and I want to start the conversation on, is how do we become quantum ready? And I mean this both in terms of being able to take advantage of the great things that quantum computing can do, because it's ultimately a force for good, but also managing the risk that it poses to the encryption of our data. And there are already groups that are starting to think about this. For example, Quantum London are a group of professionals who are already thinking about the business impact of quantum computing and who have helped set this event today. And so if you want to be part of that discussion and see where that goes, there'll be some links in the chat where you can join and see what events that they're putting on.